In this lesson, we're going to look at Euler's method, which is a numerical method, first described by Leonhard Euler, the mathematician, to numerically approximate the solution curve to a differential equation with a particular solution here. The reason why we need this method is that in the 18th and 19th centuries, when mathematicians tried to come up with different techniques to solve differential equations, just like the ones that you have done before, like using separation of variables, using the homogeneous, the substitution of v equals y over x, and also integrating factors, but eventually they hit a dead end. Okay, so they needed another way to try to look for the particular solutions, as differential equations have a lot of real applications that are very useful in science and other models. So let's look at how the Euler's method works. The Euler's method uses an iterative procedure, meaning that we'll be using some sort of a recursive formula to come up with a polygonal approximation to the solution curve. So we are going to use first order differential equations, and these first order differential equations are functions of x and y. So first, in these iterative procedures, you're going to select a step size h. So essentially, if you look at the graph on the right or at the bottom of your notes, we are going to mark off x values, intervals of x, at equal intervals h, or somehow you can also call these delta x. Okay, and then we'll also consider the gradient of the tangents to the curve at each position of x that we have. So consider at x0, x0, the starting position that we have marked off. The gradient of the tangent can be, described as y prime of x0, but also if you go back to grade 9, slope of a straight line is delta y over delta x. So delta x obviously is h, and delta y is really the function at x0 and the difference of the height y value when the function is at x1. But I can also describe x1 as position x0 plus h. Okay, therefore we have this formula over here. If I rearrange this relation, then I can isolate the new y value, okay, the new point on that approximation of the curve as y prime times h plus y of x0. So basically, we are coming here, starting from y of x0, right, the y value here, plus delta x multiplied by the slope of the tangent at the current position. More simply, as a summary, then any new points that are constructed along this new estimation curve can be found using the new position x in position n plus 1 is taking the previous x position xn plus h, and the y coordinate of the next point, y at n plus 1, comes from yn, the current y value, plus delta x or h multiplied by the derivative, right, of the function. But don't forget, we actually defined dy by dx, the derivative of the function, as f of x comma y. We use this notation, all right? And eventually, if you look at this example here, what this method does is we're using the gradient of the tangent at each new point to kind of correct the direction of the line segment so that it keeps following the curve as we progress from left to right. Take a look at Investigation 8 on page 546 in your textbook. Here we're going to consider the differential equation dy by dx of y prime equals to 1 plus x, and the initial condition that y of 0 is equal to 1. So notice how this equation, or this differential equation, is written in the form of f of x and y, and that you have f of x comma y equals 1 plus y itself. So we're going to make use of the recurrence formula that we just discussed and a step size of 0.5 to solve the equation numerically. So first we're going to construct and fill out this table of values. I have duplicated this table of values in decimals on the side here as well. So n represents the number of iterations that we have. So in the chart, it asks you to go from 0 to 5. And then the initial value we're told is 0 and 1. Yes, y of 0 equals to 1. So that's why x0 is 0, y0 is 1. And then according to the derivative, the gradient function, 1 plus yn, which is the value of 1, gives you 2. Okay, so this is how we arrive at the values in the third column. Using a step size of 0.5, obviously x1 now is 0.5. And then the recurrence formula says to calculate the next y value, we take the current y value, which is 1, and then we add it to the step size 0.5, multiplied by the tangent gradient of the last point, which is 2. So that's how we get this calculation, which works out to 2. So we have the point 0.5 and 2 as the next point on the approximation curve. And then what is the value of the gradient at this point? 1 plus 2 is 3. So that's basically how it works. So next increment, we step up by 0.5 again. So we're at 1. And then the y value now becomes, take the current y position 2 plus 0.5 step size multiplied by the last gradient. So 3 times 0.5, that's 1.5 plus 2 is 3.5. I'm going to enter that into decimals. Let's work out this current gradient. The formula is 1 plus 3.5, so that's 4.5. Okay, next step is 1.5. The y value again, we take 3.5 plus 0.5 times 4.5. And then whatever value we get, it should be 5.75. It becomes y1, so 6.75 plus 1. Okay, we are at 2 because 0.5 higher. What do we take? We take the last y value, which worked out to 5.75, and then you add 0.5 multiplied by 6.75. Okay, and then with that value, you add 1. Using my calculator, I know it's going to be 10.125. Okay, and then next, you're at 2.5. This is iteration number 6, or n equals to 5. Okay, you take this, you know what, I can make use of decimals. Okay, so that's 9.125, right? So 9.125 plus 0.5 multiplied by 10.125. Okay, and then let's do this again. This is 14.1875, so this must be 15.1875. And this is the last entry in the table required. The points are now plotted on this graph here. I can make some changes to this graph. See if it shows up a little better. What's our highest number? That was, let me make it 20, and then we make this -2. Okay, and I don't really need the minor grid. Okay, so this is the function that we have so far. The next question in this investigation asks you to select an appropriate analytical method and solve the differential equation dy by dx equals to 1 plus y. Pause the video and try to solve this equation first, and then resume it to check your answer. Okay, so here it is. According to this equation, I can rearrange it into y prime minus y equals to 1. So now you recognize that this is a linear differential equation, which we can solve using an integrating factor method. So taking the coefficient of y, which is -1, we put it in the I of x formula, and then multiply every single term in your original equation by the integrating factor of e to the power of -x. And then take your steps. You also was given an initial condition of 0 and 1. You can use that to find the value of c, which is 2. And you have this particular equation as the solution, as the actual solution to the differential equation y prime equals to 1 plus y. If you plot this function, it's the blue line shown here on the screen. Okay, so if you compare the approximation that you found, which are the green dots, and the actual solution to this differential equation, you're not that far off. So by plotting the function that you have found in 3, we have completed number 4. And number 5, you're just comparing the table of values of the actual function to the first table that you have found, which is another way to verify that how close or how not close the approximated curve is to the actual solution to the differential equation. Now pause the video and take some time to complete step 6. You're basically doing the same thing as what you have done in number 1, except this time you're taking a step size of 0.1. So every time x goes up by 0.1 rather than 0.5, okay? You can resume the video once you have completed to check your answer. So whether you have used a program or a spreadsheet or manual calculations, I hope you have done part 6. And if you have done everything correctly, you would have arrived at this table shown in my decimals chart. So those are the values. And what I'm interested in is the x3, y3 columns. Okay, so let me make this bigger. And as you can see, the red points here, this time, the Euler's method used because you're using a smaller step size, look at how much better the approximated curve is compared to the result that you found according to the green dots here. So your red dots, by using a smaller step size, you come to a closer approximation to the real solution curve to this differential equation. In other words, we can say that a numerical approximation to the solution of an ODE can be much stronger if you take smaller increments. So now let's take a look at another example using Euler's method to solve or to approximate the solution of this differential equation at x equals to 0.4. So we know that in order for us to use Euler's method, we need an explicit differential equation with dy by dx isolated. So let's rearrange this equation first. So dy by dx must equal to sine x squared and then plus y squared. This is the gradient, right? So the gradient function, we're going to put it in the last column. So here we're going to take the current x value, so xn, square that, sine it, plus the current y value, yn, square that according to the definition of dy by dx. And then the step size that we're going to use is h equals to 0.1. We're interested in knowing what is y when x is equal to 0.4. So this is kind of like the ending, okay? This is the end of the iterative process, so to speak. We know that the setup will include, well, for sure, 0, 1, 2. Let's see, what does that mean? We're starting from 0 and the initial value is 1. It is found here, okay, given in the question. This is initial value, this part here. Okay, so I'm going to mark it off. All right, so according to the y prime, let's work out what the y prime is here. I have sine of 0 squared plus 1 squared, sine 0 is 0, so 1. Okay, the next iteration, we are at 0.1. 0.2 is next, and so on. Okay, so and then 0.3 and then 0.4. So let's work out yn. According to the recursive formula, y of n plus 1 is calculated based on y of n plus the step size h multiply by y prime of n. So here we go. Taking the last y value 1 plus 0.1, our increment, multiplied by the last gradient 1, I have 1.1. And then y prime in this case is going to be sine of 0.1 squared plus 1.1 squared. Using a calculator, I've previously worked out this number. I get this, okay? Keep all the decimal places on your calculator and keep recalling the answer to make sure your final answer is as accurate as possible. So next y value, we take 1.1 plus 0.1 multiplied by 1.2199, that number on your calculator. This gives you 1.2219 ... if you work it out. And then here we go, sine, this time my x value is 0.2, my y value is 1.2219. ... squared, which works out to about 1.5332 ... and you repeat the process. So 1.2219 ... plus 0.1 times 1.5 this time. Okay, and then you get 1.37-ish. And then the next value you have here, I'm not going to show the substitution. So you take sine of 0.3 squared plus 1.37 something something squared. It works out to about 1.9814 ... And make note of this, right? We said that we want the y value at x equals to 0.4. So this is going to be our very last iteration. It's good news. So now we take 1.37 blah 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 plus 0.1 times 1.98 blah blah blah, and we get 1.573-ish. Okay, and as a result, it's a good habit to write out what we found, and therefore y value when x is 0.4 is approximately 1.57, rounded to 3 significant figures. Okay, so let me put a note here. Make sure we keep all the digits on the GDC. Okay, do not round until the end. Okie doke.